Thank you. So can everyone hear me? Okay. So I'm Pingzhong. I'm a faculty member at Tsinghua University. And in this talk, I'm going to talk about the role of priors in mechanism design. So there is a trend and a large body of literature in this conference on talking about Wilson's principle, which says that mechanism design should develop in a way that depends less and less on priors. These people confront the issues directly by analyze how bad can prior dependence cost us, okay? So this is a joint work with my students Yulong Zeng, who just defended his PhD, but wouldn't be able to come here because of visa issues. So what do you mean by visa issues? So I'm going to explain it a little bit. So when China AI researchers apply a US business visa, so there are three possible outcomes. So the first is that you will get a 10-year visa and you will get it within 3 days. And the second is that you will get a 1-year visa, but you will have to go through a 5 weeks check, which is the case for Yulong, so Yulong wouldn't be able to come because you know this check period. And then you will probably get rejected, but that decision is immediate, okay? So as far as this talk concerned, the mechanism for the US consulate is as follows. So it will take an application file as action for this time, but it also implicitly has a prior. The prior contains all the previous applications that you sent to the US consulate. And as far as I'm concerned, this prior mainly describes how sensitive your major is. In my case, how AI I am, how AI my student is, and then taking the two inputs into consideration and then output a decision for your visa, okay? So the difference between me and my student is that I manipulate a little bit. So in the previous files submitted, I intentionally skip several AI conferences. For example, if we have EC this year and triple AI this year, both in the States, I will apply for EC, I will use the EC invitation letter to apply instead of triple AI invitation letter. And my students just attend every AI conference and submit the invitation letter. So in the prior of the US consulate, they think my students are more AI than I am. So that's why he get a 1-year visa and get a 5 weeks check. And the funny thing is that if you attend a autonomous driving conference, you will probably get rejected. I don't know what's the policy here. So the previous example raises a central question in mechanism design, so which is where do priors come from? Specifically in the previous example, in the visa problem, the priors is computed from actions, from previous actions. And I would say that this is like prevalent in the sponsored search literature, as most search engines compute the prior distributions from past bits, okay? And the main message that this talk wants to deliver is that this kind of mechanism is susceptible to manipulation. By manipulation, I mean players have incentive to choose suboptimal actions in order to form a better prior in the future, okay? So that they can benefit in the long run. Okay, so this talk, we will use auction as a running example to illustrate the problem. So the assumption here is that the valuation distribution is learned from previous actions, okay? And we are going to analyze this type of prior dependent mechanism. And I want to mention that this follows from a large body of literature on using samples of past bits and samples of past valuations as input to design mechanisms, okay? So I will explain the main idea of the paper using an example of Myerson auction. So consider a standard single item auction then we have two independent bidders. And there is a ground truth on valuation distributions. So two bidders are from uniform 0, 1. Okay? And by the standard assumption of mechanism design, this is a common knowledge shared among auctioneer and the bidders. So the auctioneer knows the distribution, and the bidders will bid truthfully because Myerson auction is dominant strategy truthful. And we know that the expected utility is 1/12 for each bidders. So nothing fancy, very standard stuff. Now consider the setting in this paper. So we know that so in this example, we still have a ground truth distribution, which is the type distribution for the bidders. But here, we don't assume that the auctioneer knows this prior. Instead, he's going to learn this from the interactions with the bidders. So knowing that the auctioneer don't know the priors, the bidders decide to do something different. For example, the two bidders wants to bid this distribution. So the first bidder still bid truthfully uniform 0, 1, but the second bidder changed his bid to a constant distribution of 0 plus, which means 0 plus some small positive number. Okay? Now let's see what happens. So after the mechanism runs for a while and the two bidders stick to these two distributions, then the auctioneer, knowing that the auction is truthful, update his prior distribution to this two bid distribution. Okay? And then we will get a Myerson auction running on these two new priors. And the expected utility becomes 1/8 and 1/4, so which improves upon previous case, right? The previous case is 1/12. Okay? And this player has more utility than the truthful one. And we will show that later that, in fact, bidding uniform 1/4 to 1/2 is an equilibrium in the distribution reporting game that I just described. Okay? So the two players will bid according to the distribution. The priors are these, and they will get 1/6 utility for each player. And if you are sensitive to the numbers, you know that 1/6 is the expected utility of both second prize auction and first prize auction for the true distribution. Okay. So this is payoff equivalent to first prize auction under this true distribution. And the main results in this paper shows that this is no accident. So this is a general theorem. Okay, so I will describe the model in more detail. So we have an induced game. So the induced game is with respect to any prior dependent auctions. Okay? So we have a ground truth. The bidders know the true type distributions, but the distribution is unknown to the auctioneer. And the auctioneer first announces auction format, commit to an auction, and each bidder commits to a fixed bid distribution, so commit to a bid distribution. And then the third step is that the auctioneer takes the bid distribution as priors and run the corresponding auction. So the resulting utility is computed in an auction that takes the fixed distribution as priors, while the bidders bidding the fixed distribution as actions, but the value of the item is evaluated at the true distributions. Okay? So some notations before we get to the main results. So we have a single item for sale, n bidders, and each bidder has a valuation VI and bid BI, VI, and we use quantile. So quantile is the percentile of the value V in the distribution F. And we have a value distribution, so this is what I call the true distribution, and we also have a bid distribution, which I call the fixed distribution. Okay? And the bid action is first to choose a bid distribution BI, and the bidder will also tell explicitly that how to map from this distribution to this distribution, from quantile to quantile. So for example, if you are in quantile Q, your valuation is VIQ, and you are going to bid BI phi IQ. Phi is this mapping that tells you how to map from the original distribution to the fixed distribution quantile to quantile. Okay? So the first lemma is that you don't have to worry about this mapping. So it will always be the case that it's optimal for each bidder to bid phi IQI equals QI, which means that you will map the lowest quantile of evaluation to the lowest quantile of your fixed distribution, and highest quantile to highest quantile, okay? So you don't have to worry about the mapping. Now let's do a quick warm-up. So let's define prior independent auctions as identical among all priors. So W is the prior, and M is the mechanism. So it's identical among all the priors. So for example, second price auction is a prior independent auction. And it's a dominant strategy for each bidder to simply bid BI equals VI. So you cannot fix your distribution in a prior independent mechanism. Okay? So let's come to the main results. The main results is about Myerson auction. Okay? Myerson auction is defined as choosing the bidder with the maximum positive virtual bid. And the main theorem says Myerson auction in the fixed distribution setting that I just described is strategically equivalent to first price auction in the standard setting and the same true distribution. Okay, so this is consistent with the previous example I just described, right? Okay? So notice that this is strategic equivalence. So this is the strongest form of equivalence between games. So this implies revenue equivalence, payoff equivalence, whatever kind of equivalence you want to have. So in other words, the revenue of Myerson auction reduced to first price auction in the standard setting. So you spend all your trouble finding data, designing prior dependent mechanisms, and then you can only get a revenue for the first price auction. So let's see the proof. So the main observation here is that the interim allocation of Myerson only depends on the virtual value. Okay, not the whole fixed distribution, but the virtual value of the fixed distribution. So that is to say that if you have two virtual value phi 1 and if you have two distribution that has phi 1q equals phi 2q, they will result in the same interim allocation. So with this observation, we can write the interim allocation rule as a function of phi q. So phi is the virtual value function instead of q. Okay. The second step is that we can rewrite the utility function of each bidder in the fixed distribution model of Myerson like this. So this is by standard payment identity, okay? Now if you stare at this formula, you can see that this is a probability. So this is an interim probability that depends on this function. And this is the true value, and this is also the virtual value, right? Now I want you to switch the understanding of this function as a bidding function in the first price auction. Okay? So you consider this to be a bidding strategy in first price auction. And this is exactly the definition of the utility in first price auction. So this is the probability that you get allocated with this bid. And this is your value minus your payment, right? This is the utility gain that you from winning. So the winning probability times the utility gain. So this is exactly the utility function of first price. When you bid, the virtual value in the Myerson auction. As a result, these two games are strategic equivalent. So here you report a fixed distribution which induces a virtual value. There you just beat a bidding function. Okay, and they share exactly the same utility function. So which means that these two games are the same. So these are strategic equivalents. And we have a summary of other results. So we show that Myerson is equivalent to first prize auction. And we also show that, so these are more technically involved, but we managed to show that second prize auction with monopoly reserve is revenue equivalent to second prize. So you have a reserve and under the fixed distribution model, the effect of reserve is gone, okay? And here we assume IID and regular, but for these two, we just assume IID. So this is second prize auction with single sample reserve, which also appeared several times in the literature. This is even less than revenue of the second prize auction. And we also define a very general form of virtual efficient auctions, which means that you always maximize some kind of virtual values, but the virtual value is defined broadly. And yeah, so all these results suggest that the revenue of prior dependent auctions may not be as good as you expect it to be. So just a quick summary of the takeaway message of this paper. So we have a model that evaluates the damage of prior dependence. So it can be regarded as a quantitative model for Wilson's principle. And the results imply that the revenue of the prior dependent auctions may not be as optimistic as theory predict to be. Okay, that's it. Yes. Some cost of what? Some cost for lying in the distribution. I don't know. So it's a different game.